the 9 a.m. class can probably vouch that this workshop is slightly hard. I'm not going to lie to you. But I've found a way like to structure like the questions that's like a bit different to what we've been doing in previous weeks, but I hope that it's effective to teach you all the content. Because unlike last week, hopefully you saw the recording, or if you haven't had a chance to look at the recording, just make sure that you can find it, because I think that's a very important week's worth of content. But yeah, as opposed to that week, which basically was just playing around with one big formula, this week has a bunch of smaller formulas, but it's just the pure amount of formulas that you'll encounter. It will remind you a little bit of soil mechanics. Okay. So how I've structured my notes, if you'd like to go through them, there's a copy of them. There's also a mailing list if you want to be sent the videos, recordings of each week. So if you want a copy of my notes, it's there on the screen right now, because I usually go slightly quick. So page 2 to 10 of my notes here is just going to be running through the notes and formulas as usual, and then page 11 to 17 are my work solutions in order, right? So this is good for you guys if you want to print out my notes, or if you want to go back and look at the work solutions in order. But how I'm actually going to do the lesson is going to be a little bit out of order. It's going to jump back and forth between content and worked example. So that's why I've done it like this. By the way, the workshop questions, if you're not aware, are at the back of the geotech booklet. At the very back, pretty much. And you might see, like, as you're looking through the content of those notes, there's like example like S1 or S2. Those are the lecture examples. So you'll get the solutions by watching the lectures for those, essentially, right? Okay, but what we're going to do at the very start here is we're going to do a quiz for week 7, which was last week's content, right? So if you haven't had a chance to do this, like to watch that recording, that's completely fine. You can still have a crack at this quiz, because a lot of it is just like trying to use your common sense to the best of your ability, so you understand the physics behind the equations, right? So we'll start with that. That's a little bit of a recap. Hopefully getting everyone onto the same page in terms of bearing capacity for shallow foundations. But yeah, today's focus later on will be on the settlement of shallow foundations. I'm not going to lie to you, this quiz is going to be slightly hard. So if you haven't watched, if you have watched my recording from week 7, aim for about 2/3 of the questions getting it right. If you haven't, aim for about 1/3. Okay, that's what you're going for, right? Has everyone who wants to scanned for this? Okay, let's give it a crack. Congratulations to these people. Job to say. This is the PSM round 2 interviews. Okay. Yep. So some of you are okay, and some of you aren't. But for those of you who aren't, this will be good character development for you for the next few weeks. Because only going to get harder. Right. But basically, for shallow foundations, we're talking about all these types of footings other than piles. So piles are considered deep foundations, and that's what we're going to be tackling next week. Got it? Yeah. What else is there to talk about? I mean, the majority of foundations, I think all foundations for buildings or structures are going to be made out of concrete. And the reason for that is because concrete is a very durable material. It doesn't rust like steel, it doesn't rot like timber. And there'll probably be reinforcement within this concrete. So you'll learn more about that in concrete structures when you do that. But in week 7's content, we're just dealing with the strength of the soil underneath our footing, right? So it's kind of the strength just before it starts to slip and do all that stuff, right? So, yeah, let's just move on. So Hansen's equation is the big equation that we use for basically every question in last week's content. And the idea is that it has different notation for a bunch of different letters, right? And so in the context of Hansen's equation, we use, let me just draw out general case for a footing like this. Right. This is the soil surface. The depth that we care about is essentially from the soil surface to the base of the footing. That's what D is here, right? So we also call this dimension here B, right? And if this is a strip footing, essentially it runs into the page like that, right? And the L dimension would go into the page. It's supposed to be the longer dimension. And for a strip footing, that's much bigger than the width, right? The other thing to note is that lowercase d, right, refers to the depth from the bottom of the footing to groundwater, water table, right? Water table, right? So yeah, that's where all these numbers come from. Yeah. So essentially, the way that it works for groundwater analysis, right? Oh, by the way, in Hansen's equation, we have to calculate Q, right? Q naught. That's the soil surcharge, and we also have to calculate gamma, which is the unit weight, right? And essentially, Q naught, or the soil surcharge, is a function of the depth from the soil surface to the base of the footing. Like, whatever number you're going to get there is going to be to do with how the water interacts with the soil here, right? Whereas gamma is going to be a function of how the water interacts with the soil here. Right? It's a little bit more complicated than that, but that's the general case, right? So, yeah. One other thing that's happening in this particular question is that there's eccentricity. Okay. So eccentricity is basically load offset. Okay. So if your load is being applied like that on a footing, that's the center of the footing. Your eccentricity is your offset, like that, right? And if this is the width of the footing, call it B. B dash is our effective width, right? And the effective width has a formula. It's the regular width minus 2 times the eccentricity. The idea behind this is that this area of the footing is our effective width, kind of. So you reduce the total width of the footing based on how it's loaded, okay? So, yeah, essentially, if you've never seen this equation before, it's here in your notes. So in page 17 on the physical booklet, you have to consider the effects of groundwater. Okay, so if the water table is really far beneath our footing, you can essentially just use gamma T for drainage analysis. Like, groundwater is not going to really affect your footing. And if a water table is at or above the base of your footing, you can use just gamma dash. That's your submerged weight. That's basically your weight minus the buoyancy force due to water, because it makes it like lighter. So if you've been like, obviously everyone's been swimming before, but in the water, it doesn't feel as heavy, right, when you're floating around versus when you're out of the water, right? That's what's happening for your soil as well. So that's the submerged unit weight. It's a weight that's less than the total unit weight. The idea is that if the water table is in this kind of region that's in between these two cases, you have to interpolate it in some way, right? You have to partially account for the fact the effects of groundwater, and that's what that equation there is for, right? And it's relative to the effective unit weight. So in that question that I asked you guys, our effective unit weight, B dash, is going to be 4 meters minus 2 times 1 meter, which was the eccentricity. So it's 2 meters. Okay. And yeah, and then D is 3 meters, right? Lowercase d. And since the depth is further down than the effective width, but beneath the footing, we don't have to account for the effects of groundwater, right? Does that make sense? That's probably the hardest thing to understand about last week's content. Yeah? Okay. Yeah, okay, you know what? If you have questions, ask me later, alright? Okay, so in terms of the Hansen equation itself, it's this really long thing, right? And if you've never seen this before, like say you didn't watch last week's lecture, you'd be like, what the fuck, right? So the idea is that it looks like a really scary equation, but it's not too bad because you actually cancel out the majority of these factors. And knowing what to cancel out and where is going to save you so much time. So that's what these questions are designed for. So in this particular case, we can cancel out a couple of things. The inclination load factor, which is I, is to do with how your column is loaded. Sorry, this isn't a very good... Yeah. The inclination factor is if your column is kind of diagonally loaded like that. But since it's not diagonally loaded, it's loaded vertically, we can just cancel it out. All the inclination factors become 1 in your equation, right? The ground factors are to do with whether you have a slope next to your soil, next to your footing in the soil surface, right? That angle there. Since it's flat, again, we can cancel out the ground factors. Base factors is if your column itself is on an incline, like that. That angle there. So since it's none of these cases, it's just the default case, we can just cancel out the I, G, and base and B factors, right? That's where that option comes from. Cohesion, right? Cohesion, as we talked about in week 5, is to do with the fact that we're dealing with sand. Let me try to zoom in like this. We're dealing with sand, and we're given that it has like these material properties of friction, but not of cohesion. So cohesion is kind of a clay property. So since the cohesion of this soil is effectively 0, we can actually cancel out that C term, that becomes 0, and that entire term there is actually crossed out. Got it? So in this more extreme case, we can actually cancel out everything. Okay, I'll tell you why. So before, we were dealing with an individual footing, right? So that's a square footing that's 1.5 by 1.5 meters, right? In this case, we're dealing with a 1.5 meter strip footing. So strip footing is like this, it runs into the page. And the good thing about strip footings in the Hansen equation is that all the S factors cancel out and become 1. Got it? So that's why S cancels out for strip footings. The depth factor, right, and the soil surcharge are both functions of this depth. So if your footing is on the surface of the soil, D is 0, right? And when D is 0, you won't have any soil surcharge, and you also, all the depth factors will cancel out and become 1. That's why all the depth factors are cancelled out on the left here, and that's also why soil surcharge is cancelled out. And same thing applied from before, because it's just the modified version of that other question. Does that all make sense? Okay. Lastly, it's this here, right? So this is an additional step you have to do when you're dealing specifically with loose sand. So if the question is like loose sand, you have to modify your material properties, your cohesion and your friction angle. Okay. Yeah. So that's purely just a special case for loose sand. Okay. Does anyone have any questions about that? If not, we will move on to the week 8 content. Oops. Okay, so for anyone who missed it, here's a copy of my notes. So if you scan that QR code on the left, you can follow along. Again, I usually go a little bit quick. And if you want to join the mailing list, that's on the right there. If you've already scanned the mailing list one, it's the same link. I just email everyone on that list the recordings of my workshops, right? Okay. So let's talk very generally first. So settlement is different to what we've been doing, because what we've been doing is calculating the strength of the soil before it fails, right? And here we're actually calculating the settlement of the soil now, right? So it's to do with the amount it displaces. Okay. Here on the left here, we have load versus settlement. So this is very similar to kind of a stress strain graph, but it's what they use kind of for soil instead. The idea is that there'll be, for last week's content, we had like ultimate capacity and the safe load, like the allowable load. And here we'll have some sort of max service load, but that's actually usually not what we're calculating. What we're usually calculating is the settlement, okay? The reason for this is that most of the time you're given some sort of Q in the question, and you have to work out the settlement instead for these using these equations, right? So let's talk about the different types of settlement. There's 3 types of settlement. The first one is called the elastic or the immediate settlement, and this is very important for sand, right? The next one is the primary or the consolidation settlement, and this is important for clay. So in terms of like what order these things happen in, it goes top down. So the immediate settlement happens first. You can just for the sake of numbers, you can say this happens all within 1 day, right? And then your primary consolidation settlement happens next. You can say this happens within like 28 days, just to give you a number, right? And then for secondary or creep settlement, this is your very long-term settlement. So it could be in the range of like 5 years, 50 years, something like that, right? So yeah, and it kind of plateaus. So I'll show you a graph, right? That's how it's broken up. The initial settlement happens here, that's your elastic settlement, and then consolidation settlement happens next, and the creep settlement just keeps happening. right? But it plateaus, you know. Okay. Yeah, does that make sense for everyone? Okay, cool. So what we're gonna do is I'm gonna jump into the first question I'm gonna do, which isn't question 1. So if you're following along on your notes page, on your printout, it's question 3 at the back of the book for settlement of shallow foundations, right? I think this is the best question to start with. That's question 2. Oops. Question 3. I think this is the best question to start with because it starts with elastic settlement, which I think is theoretically easier to understand. Oh, sorry. I haven't gone over elastic settlement. Let me just quickly do that. Okay, here it is. So, elastic settlement is dependent on your footing shape. Okay, so if you have a strip or rectangular footing, you use the formulas here at the top, right, and the charts here at the top as well. If you have a circular footing, you have to use this formula at the bottom and this chart at the bottom, these 2 charts at the bottom. The good thing about these charts is they actually include a little diagram regarding what they're talking about. So if you ever forget how to use them, there's almost like a little instruction diagram at the top, right? And the other thing is it also includes a formula you need to use it in, like on the graph. So space-wise, it's pretty efficient. But anyway, let me just pull up my notes quickly. Okay, let's talk about all the components of this formula. Okay, so let's break it down. So Q is the footing pressure. Again, you're given this in the question, and if you're not given this, you're given P, and P is the point load acting on your footing, and then you just divide that number by your area of your footing, okay, and that's how you get Q, right? B is your footing width, right? So footing width is that least dimension there, okay? Next, we have Poisson ratio and elastic modulus. So it's probably easier to go over elastic modulus first. By the way, does anyone need a photo of this? Because I'm going to rub it out. That's for the week 7 stuff. Okay. Okay, let's just quickly talk about elastic modulus for any material, right? So do you remember stress strain graphs? These just describe, they're like little curves on this little graph that describe how a material behaves, and the line varies from material to material. For soil, we usually just care about its compressive properties. You squash the soil down, right? So we're looking at compressive stress. It might look something like this, for example, right? The idea is that this region here is your elastic region. So if you have an elastic band, right, the reason it's called an elastic band is as you pull it and let it go, it just returns to its original shape, right? So that's what elastic materials are. They aren't permanently deformed, I guess, right? And that's described by this straight line here, right, here. And so the slope of that line is, slope is going to be E, right? That's what elastic modulus is. So the idea is it has a predictable slope, right, for this entire region here. Got it? Whereas after you pass the elastic region to the plastic region, it's going to be non-linear, right? But the idea is, since we're dealing with elastic settlement, we just care about elastic modulus in this part of the material curve, okay? Anyway, that's what elastic modulus, that's what Young's modulus is. Poisson ratio. Imagine you have like this soil mass, right? Just made up a bunch of soil. and you push it this way, right? You apply some load to it, and say it settles 1 millimeter, okay? The idea with the Poisson ratio is it's almost like a squash ratio of how much it's going to expand outwards after that, right? So this amount and this amount added up, right, is going to be, for example, 0.3 millimeters, right? So you squash it down 1 millimeter, it fattens out 0.3 millimeters. That means you have a Poisson ratio of 0.3. That's what Poisson ratio is. Okay. Yep. So I'm just going to do the question now. So again, if you're following along, it's question 3 in the notes. The difficult thing about this question is it doesn't give you this diagram which I've drawn down here. You kind of have to make the diagram yourself, okay? And reading through the question, it can do your head in a little bit, right? So we have 2.4 meters of sand overlaying rock. That's what I drew here. So 2.4 meter soil layer. Specifically it's sand, so we know that we have to kind of use our elastic settlement formulas, right? There is no water table, so that's all good. We don't have to account for any water effects. A plate loading test is conducted at the site using a 0.3 by 0.3 meter plate, okay? So what a plate is a plate isn't structural. A plate is just like a miniature footing that they're gonna put there in order to derive material properties for the soil. Right, so it's like a very small scale footing. It's like a simulated little model that they put just to understand how the ground works around there, right? It's 0.3 meters below the surface. So on the right here, I've drawn what the plate dimensions would look like, right? When a pressure of 150 kilopascals is applied to the plate, we know that it settles 0.84 millimeters, okay? The full-size footing, right, is 2 meters by 2 meters, and it's going to be built at a depth of 0.4 meters below the surface. It's going to receive a pressure amount of 250 kilopascals, and we have to determine the amount of settlement that this footing is going to endure, I guess, right? So what I've done first is we actually know more information about the plate. That's how it generally goes. The plate is there because it's got like a little like gauge. I don't really know how it works, but like it has a little gauge that tells you how much it settles by and how much pressure that you put on it, right? So we're gonna try to back figure the elastic modulus of the soil based on the plate numbers, okay? So again, here are all the plate numbers, right? D, as we've gone over, similar notation to Hansen's equation, is 0.3 meters, right? B is 0.3 meters. B is the that dimension there. L is 0.3 meters, and L is 0.3 because remember, we're not dealing with a strip footing, we're dealing with a square shape, right? Oh, sorry, not footing. We're not dealing with a strip plate or anything like that. We're dealing with a square plate. So B and L are going to be the same number. They're 0.3 and 0.3, right? Okay, so what's H? So H is kind of new. H is the distance from the base of the footing, or in this case, the plate, right? So the base to our rock layer. So we're told that the entire sand layer is 2.4 meters like tall, right? And so the depth from the base of our plate to that rock layer is going to be 2.1 meters because we know that the plate is 0.3 meters into the ground, right? Make sense? That's our H value, okay? We're going to be using H throughout this whole workshop, so just make sure you understand that, right? Okay, so now what we have to do is we have to calculate 3 ratios, right? The D on B ratio, the L on B ratio, and the H on B ratio, okay? right? These aren't hard ratios to calculate. You literally just plug in all those values that we know. So 0.3 divided by 0.3 is 1. L is 0.3 over 0.3, that's 1. 2.1 divided by 0.3 is going to be 7. Okay. Sorry, what's it? Yep. Okay. Now we pull up, this is our equation that we're going to be subbing all our numbers into, okay? Wait, did everyone get that? Okay. This is the equation we're going to be subbing in all our numbers into. So this is the equation specifically for square or strip footings, which also applies to plates, okay? So first we're going to figure out these constants. This is mu1 and mu0, okay? I'm going to zoom in here, right? So our H on B ratio was 7, right? So 7 would be somewhere like here, maybe. And we go up until the line, right? So these lines are represented by L and B. L and B is 1, right? So we're referencing this line. We go up until we hit the line, the curved line, and we go all the way to the left here. Okay, now we read that number. Just in your head, what do you think that number is? You're trying to calibrate it based on what the solutions say. So I'll tell you what the solution says. Mu1 is 0.7. Okay. Next, we'll do the same thing with the bottom graph, which is for mu0. So D on B is 1. And we go up until the line which says 1. Okay. Again, we'll do the same thing. So what do you reckon this reads as? 0.73. Okay. So these are the numbers we're going to be plugging into this equation, right? So what we're doing is we're calculating the settlement of the plate, right? So we were told that we put 150 kilopascals of pressure on the plate. Right? We're told that the plate is 0.3 meters wide. We were told, actually I probably didn't mention this, but we were straight up told the Poisson ratio for the soil is 0.3. Okay, but that's just given in this question. Okay. And all over the elastic modulus, which is actually what we're working out. So I'm going to leave that as E. Okay. I'm going to move this across. Mu0, 0.73. Mu1, 0.7. Okay. We're actually also told that the settlement of the, we're told the settlement of the plate, right? So in the question, we were told it was 0.84 millimeters, right? So the reason why I've written out the units here is you have to be very careful with the units and make sure we're dimensionally consistent, because since I have meters on the right here and millimeters on the left here, our elastic modulus isn't quite going to work out the way that we want it to. So what we have to do is we have to convert these to the same units. So what I'm going to do is I'm going to convert the millimeters to meters here on the left-hand side. The millimeters cancels out, and we get 0.84 divided by 1,000 meters. Right? We're going to use our algebra to just move E onto the left-hand side, everything else onto the right-hand side. Right? That's going to give us our elastic modulus. When I plug that into the calculator, it gives me this. So we are given our elastic modulus in kPa. Okay, so that's this value in kPa, and the reason why it's in kPa is because our pressure was given in kPa, right? So this might seem like a weird number to you if you've done steel or concrete, But the reason for this is because soil is a lot less stiff than steel and concrete. So this is actually a reasonable number. For something like concrete, yeah, elastic modulus would be like 32 MPa or something. No, yes, 30. Yeah, anyway, steel a lot bigger, concrete a lot bigger. Yeah, but this is realistic for soil. So for our footing, now that we know the, yeah, sorry. Yeah, question.
What is that question? The E dash and D.
Oh, right. Effectively, in this equation, yes, because we're dealing with sand, right? Oh, sorry. Okay, sorry. There's a bit of context here. We're assuming that the entire layer of sand here, the 2.4 meter layer of sand, is uniform in terms of its elastic modulus, and we don't account for the effects of groundwater. So we just add a little dash because we're doing like drained analysis, I guess. Yeah, sorry, I don't know if that's a good explanation. Because later you'll see there's actually examples where E varies with depth. It gets like more and more stiff as we go deeper in the ground. But E dash is fine to use here because yeah, we're just dealing with sand basically. yeah, sorry. And for elastic settlement, we'll pretty much always be dealing with sand. So yeah, effectively E and E dash the same thing here. Okay, we're gonna do the same thing with the footing. So what I've done here is I've written down the depth. So if you remember from before, I'm just gonna draw it out again. The footing's depth was 0.4 meters into the ground, right? Its width was 2 meters. Its length, right, because it's a square footing, is also 2 because it's a square footing. All right, now H. All right. So our sand layer was 2.4 meters tall, right? So our H is from the base of our footing down to the rock layer. Right, so H is going to be 2 meters because we're just doing 2.4 subtracted by 0.4. Got it? So H is just all of our compressible material underneath the base of our footing. Okay. All right, now we're going to do the ratios here on the left, right? So 0.4 divided by 2, 0.2. 2 divided by 2 is 1. H divided by B, so 2 divided by 2 is 1. We're going to do the same thing to find our mu1 and mu0, okay? So H on B, we follow the line up here until we reach 1. So 1 and 1. We're following this line for L on B is equal to 1. And what we're going to do is we're going to go all the way to the left here to find mu0. Okay. You guys tell me, what is this number? 0.46. All right, got it? So again, to calibrate this in your head. Next, mu0. Oh, sorry, I meant mu1 before, but now we're doing mu0. D on B is 0.2. And we go up to the line which says L on B is 1. Then we go left. All right. In your head, what's that? 0.95. Okay, it's always different to what you're thinking in your head. All right, anyway. So now we're gonna do our calcs over here. So I'm gonna move this. All right, so we just plug in everything. So the question said for a surcharge on the footing of 250 kPa. So I'm plugging in 250 here. what is the settlement, right? And then we plug in the width of the footing, which was 2 meters. Sorry, I'm going to write the units as well here. Same Poisson ratio, that's a soil property, not a footing property. Elastic modulus, this is a soil property. This is what we worked out in the first bit. Right? And we're going to plug in the mu values. Right? And we get that the settlement is 0.008 meters. So it's in meters because our footing width is in meters, right? So now we have to convert it to millimeters. So the answer is 8 mil. Okay? Does that make sense? This is the easiest question we're going to be going over today, all right? So the other methods will be a bit different. So I realized after doing the 9 a.m. class, the timing for this workshop is a little bit tight. So I've slashed out one of the questions, but what I'm going to do is I'm going to go over the theory for what we're doing next is primary or consolidation settlement, aka the settlement on clay. And then I'm going to quiz you guys with another quizzes. And then I'm going to do the question, because the question takes quite a while. And I want you guys to be like refreshed for that, okay? So we're going to go over the theory, then do the quiz, then do the break, then actually do the question, right? So for consolidation of clay, there's a few more steps. This is because it's time dependent, essentially, right? And we're dealing not with the elastic part of the material curve anymore. We're dealing with this kind of like unrecoverable plastic / inelastic material property, right? So essentially there's more steps. The first thing you always have to do is calculate the stress acting on the soil, okay? Yeah, that will make more sense when we're doing the actual question. But if you remember all of these from soil mechanics, Busenek's equation and friends, this is, they're basically for various loading cases, okay? So the concentrated point load is very similar to like 1300, a point load, right? And we care about, okay, how does this affect our point of reference in the soil? Actually, what I should probably do is I'll tell you the context of how they... So say you have a soil layer of clay that's like 3 meters, for example. They have to sample the soil and get its like properties halfway through this layer, okay? 1.5 meters down. So this is our point of reference, and that's where we're going to be doing all of these calculations too. So like, that's actually our Z value in all these formulas, okay? So halfway through our compressible clay layer. Got it? Because at the bottom here will be rock. Right? Okay. Uniform line loads are similar to point loads, but acting in a straight line into the page, right? So like, if this is your soil surface, and then we have whatever footing, let's say, that could be a point load. But going into the page, right, if it's like that, and it's one-dimensional this way, it's just a one-dimensional distributed load, where it has like no width, basically, when we're looking at the cross-section, that's a line load. Got it? All right. So again, this is just an extension of Busenek's equation, but it doesn't really correspond to a footing, right? Because a footing, this is plan view, so this is top down. A footing is like a two-dimensional shape, right? Like that we place on the ground. So we can't really apply these equations to footings. So essentially, we have some more equations for that. The first one that we really have to start talking about is the uniform strip load. That's for a strip footing. This is what we're going to use for a strip footing, okay? It's like this. And again, if we have a point of reference over here that we sampled halfway down the clay layer, we have to do all these geometric calculations relative to that point, okay? For circular area loads, we're not going to see this in this workshop, but you might get a circular footing, right? There's two methods. The first method is the simpler method, which uses the formula, and that's where you have your circular footing, and it's loaded right in the middle. It's not very good drawing. It's loaded right in the middle, okay? That's when you can use this formula. If your circular footing isn't loaded in the middle, you're gonna have to use this lovely graph, okay? Got it? That's the idea. But again, we won't have to deal with this specifically in this workshop. What we do have to deal with is our good friend Fadum's chart, okay? So Fadum's chart applies for any rectangular shaped footing other than a strip footing. That's individual footings, combined footings, or raft footings. A raft footing, by the way, could have like, for example, like 9 columns acting on it like that. But the idea is the contact with the soil is all rectangular. Okay. Yeah, that's going to make more sense when we do the question, hopefully. Okay. With an irregular area, you have to use Newmark's chart, which is even worse, right? It's even worse. So, say you have a footing, which they're not going to give you, but just say, for example, you have a footing that looks like this. That's what Newmark's chart would be, like how you would use it. And I've written some instructions here, but I also just say don't worry about this because there's no way. There's just no way, all right? Okay, cool. So that's just step 1. That's just finding the stresses on a soil, okay? Next, we're going to find the initial and final stress at that point that we've sampled, okay? What I mean by initial and final stress is before and after you install a potential footing, okay? Because this will plug into our graph, okay? This is a void ratio like graph where basically the idea is that the consolidation of clay depends on its change in void ratio. What that, if you forgot what void ratio is, it's basically the amount of air like in the little pockets between the soil. So as that gets reduced, yeah, that's what happens as your clay consolidates, right? Or like it compresses, right? And yeah, we kind of, hold on. Essentially, right? You have normally consolidated clay and you have overly consolidated clay. Oh, sorry, over consolidated clay. But sometimes you can have clay where, how do I say this? Okay, there's basically a pre-consolidation, which is this sigma-PC value, which is given, okay? That's like the tipping over point for soil. So the idea is if all your calcs fall within this range here, it's normally consolidated. If it's over here, it's over consolidated. But sometimes it can be a mix of both these regions, right? And that's why we need this formula. And that's where we have 2 straight lines to kind of work with, right? Because we want the change in void ratio. Okay. What's fun is this is going to be in the question, so get ready for that. Anyway, the idea is that the most important thing that we're trying to do here is find the change in void ratio. Okay. From the change in void ratio and knowing the initial void ratio, we can find the settlement. That's it, okay? Yeah. For creep, which we're not going to deal with in this workshop, but again, creep is that long-term kind of settlement. very similar looking formulas, but they'll just be like more time effects, which will be in the caliber of like years, which you just factor in. But it's almost the same idea. Okay, cool. So what I'm gonna do is I'm gonna give you guys a break. Break. Quiz then break. Okay, we'll do the quiz then break. Sorry. Quiz then break. Break then quiz. Okay, I'll do quiz then break so that you can rest after the quiz. But these are the main ideas I want you to get out of this workshop, all right? So it's to do with the elastic settlement, which we've seen in question 4, and the consolidation settlement, which we haven't done a question 4 yet, but I've just yapped about, essentially. All right. I think so. Is everyone in? All right. Is everyone in? Let's get started. Let's just quickly go over the questions. So, yep, we're dealing with elastic settlement first, then consolidation, and then creep. That's the stuff here. Yes. So for sand, sand calculations for settlement should be done with the elastic settlement in mind in terms of like which formulas to use, and clay should be with the consolidation formulas, which we'll see used soon. Yeah, the most important thing I want you to understand here is H, right? So H is just the distance from the base of the footing to your bedrock or your rigid, incompressible rock layer, right? And yeah, so in the question that we just saw, plate loading test, the idea is that you use the plate to determine various soil properties, such as elastic modulus, right? It's not actually structural, right? And yeah, so for consolidation, calculate your stresses acting on the soil first, the change in void ratio between these stress loading cases, and then you can find your final consolidation settlement after that. The S average, yeah, the elastic modulus and S average aren't true because that would be what you might do for sand or your elastic consolidation. Oh, sorry, not elastic consolidation. Your elastic settlement rather than your consolidation settlement. Yep. So strip footings you should be using the uniform strip load formula. Individual footings you should be using the rectangular area formula, right? The uniform strip load and point load equations don't really hold for footings because footings are quite wide. You know, you'd expect a footing to be at least 1.5 meters, and that doesn't really quite represent. That's not really quite represented by a point load. Yeah. Okay. You can have your break, everyone. So feel free to get some food, get some water, go to the toilet. Yeah, just chill, have a chat. Yeah, we'll be back maybe at like 12:20. Yes. I'll tell you what. I'm really going over this one. So basically, if you have a rigid footing, right? The stress distribution actually looks like this. Right. Oh, I don't really know why, to be honest. it just has like a bit of a weird shape. But the idea is with those formulas, they just care about the average settlement, so they kind of pretend for that. So basically, the sides here will settle more than the middle, or the other way around, I can't remember. But the S average is just like the average settlement of the entire footing will be that value. That's it.
Is the shape dependent on
I think so, slightly. But we only ever use that S average formula for sand, for elastic settlement anyway. So, like, I'm sure there's like some theory, like physics behind that, but I don't really know it, to be honest. It's more just I know how to use the formulas, and that formula is specifically for sand, for elastic settlement.
I think one of the Oh, really? Oh, shit. Are you I guess it's
I'm bouldering.
that means no.
Yeah.
I can where do you go now?
We changed like places. I'll be down. Brazilian sauce. It makes
I mean, like, if you're gonna go,
That
that's actually why I was confused, because I know you've already done one.
For every tune, I'll run through one and I'll make really mistakes. And then the 9 a.m. The 9 a.m. tune is done. And those are the hardest streets. So the 9 a.m. like 11 a.m. ones
You're pretty bummed. Did many people shop to 9 a.m.?
maybe half the amount.
Oh, half the amount of it?
Yeah.
So do you normally have to do the water?
This would be the normal amount, 9 a.m. And then 11 a.m. Oh no, well that's back in
Yeah.
So it's really hard to tell.
Okay, all my friends speak today. I checked their locations, like, oh, I hope. I almost came to this one, I was like, this is boring so hard. Yeah, it's really just like,
Oh, you're just holding on to this. I wouldn't Alright, smokers up. We're gonna do question, so if you're following, we're gonna do question 1, alright? Okay, so the hardest thing about this question is there's so much stuff loaded into this question and like the wording for the question. So I have to break it down first. And probably one of the hardest things originally for me to understand when I was working through this question is how it looks in 3D. Okay, so I've drawn here in a perspective view. One sec. Yeah, I've drawn a perspective view of what we're looking at. So they gave us a plan view and a section view. The idea is that sample point thing that I was talking about is very important because it's going to inform all of our stress calculations, right? So the sample point is on the center edge of this raft footing, right? And this raft footing is just, it's like a giant strip footing almost, right? This is like a big square. And so we're looking at that center edge, okay? And then in terms of how deep we're going into the ground, it says here 1.25 meters into the ground, which is expected because we want to go halfway through our compressible layer. Oops. So we want to go 1.25 meters down into the ground, right? We're told that the water table is at the surface of our soil, and our rock layer sits there. This is 2.5 meters. Okay, so in terms of what's happening, the raft footing, you can assume it has been there for a long time, and this is like a proposed scenario for, okay, what happens if we install the strip footing next to it, right? So what we're going to have to calculate is we're going to have to calculate the initial and the final stresses acting at the sample point before the strip footing was installed and then after the strip footing is installed. That's the general idea of how this is going to work, right? So again, these two before, all three is the stresses in our soil after, right? Installing these strip footings, installing strip footing isn't going to remove stress, it's going to add more stress onto this point, right? So again, everything is in reference to the sample point, keep that in mind. So first we're going to calculate the stress in the soil at this reference point, right? So again, 1.25 meters into the ground, right? That's how deep we're going into the ground, from soil surface to that sample point. We're told that the water table is at the surface of the soil. So the only unit weight we care about is going to be our submerged unit weight. Right? Our submerged unit weight, remember, is just the weight of the soil subtracted by the weight of the water because of buoyancy of water, lifting it up, kind of makes it like less heavy, I guess, right? So this value was given to us as 20 kilonewtons per meter cubed, and this is 9.8 kilonewtons per meter cubed. That's just a known value for water, right? It's based on gravity. Okay. Okay, so hopefully this should make sense so far, right? So the stress at that point, due to the soil we've just accounted for, now due to the raft is what we're going to calculate next. So we're going to have to use Fadum's chart and this formula. Right. So, essentially, the thing about this, like, I guess, like, when you use Fadum's chart, is that all the values you're going to get for IR, which is the influence factor, right, is going to be relative to if you took the sample from a corner of the footing. Yeah. Okay. So it's from corner. Calculated from corner. Okay. However, if we look at our loading case, our sample point, yeah. This isn't from the corner. This is from the center of the edge. However, we can split this footing into two smaller footings almost that are like back to back, right? Like we can imagine it like two different footings. And what we can do is we can do our calculations for Fadum's chart as if it was a single footing and then double it, right, to get twice the amount of stress. So we're doing like two half footings. Does that make sense? Yeah? Okay. Now we have to account for some geometry. These words might seem a little bit abstract. You might recall them from soil mechanics, but we have these dimensions which we were given in the question, right? And this is going to be equal to our m factor multiplied by z and our n factor multiplied by z, where z is the depth, okay? So we have to kind of like, our end goal is to solve for m and n, right? And we already know these values. So it's a 10 by 10 footing, right? So mz is going to be 10, nz is going to be 5, okay? Right? Our depth is 1.25 meters into the ground. NZ, we know is 5 meters, as I drew on the right. MZ is known to be 10 meters, as I've drawn on the right. We plug in Z as 1.25, and we're trying to back calculate N and M, okay? So all I have to do is divide 5 by 1.25. And I get N is 4, and M is 8. These are the values which we can now look at Fadum's chart and work out our influence factor from, okay? So, let's count these lines. So this goes up by 1. And we care about line 8. Or M is 8. Okay? We care about N is 4. So, you have to interpolate between 2 and infinity. Not quite the easiest job ever, but let's say it's here. Actually, I think it's closer to here in the answer. So basically, we have to make a line for 4, which is like kind of like here, right? What we're looking for is this value on the left here. So whatever value this is IR. Guess what this is? have a think in your head. 0.25. Yep. It's never the answer you think it is. Okay. So that's IR, that's our influence factor, right? Now we just plug in, remember the 2, into our formula. So does everyone understand why we multiplied it by 2? It's because we're doing 2 half rectangles from the corner, right? Okay. Let me do this one first. So in terms of what Q is, we're actually given Q in the question. I forgot to write this in, sorry. But we're told that the raft footing has 54 kPa of loading. And we're also told the strip footing has, sorry, I'll draw it down here, 150 kPa of loading, okay? These would be our Q values when we're assessing the raft footing and the strip footing respectively, okay? So that again, this is from the question. I just forgot to tell you guys. It's like one of the first sentences. So that's 54 kPa. Right. So it's 2 times 54 times 0.25. That gives us 27 kPa. Okay. So this is from our soil stress, and this is from our raft footing stress, and we add them together. You get 39.75 kPa. So that's the stress with just the raft and the soil, right? So before the strip footing's installed, that's what we're going to call stress initial. Okay. Everyone got it? Yeah. Here's where it gets a little bit tricky, because for a strip footing, the geometry is a little more cooked. I'm not gonna lie. Okay. So the first thing you have to realize is that from our sample point to the base of our strip footing, this is 0.75 meters. Okay. So what I'm going to do is I'm going to redraw our scenario from this cross-section view, but here's our strip footing. Here's our raft footing. Okay, so this total height was 1.25 meters. This height here, 0.75 meters, right? The distance between the raft footing, oh sorry, not the raft footing, we care about this point here, which is point X. The distance from point X to the strip footing horizontally was 0.5, which is given in this diagram here. And the width of the strip footing itself is 1 meter. I should probably draw that a little bit more accurately. Everyone got it? Yeah? So, what we have to calculate here are these angles. That's beta and that's alpha. So we're going to use rise over run, right? A tan inverse rise over run for beta, and alpha is going to be slightly harder to calculate, but I'll tell you how to do it. So beta, tan inverse rise over run. We're looking at the rise over run kind of from this perspective. It's I, right? So the rise is going to be 0.5. And our run is going to be 0.75. Got it? When we plug that into our calculator, that gives us that beta is 33.69 degrees. That's beta done. That's not too bad. So, how can we get this angle alpha? There's two ways to do it. The first way, using either sine or cosine rule from high school, which I don't expect anyone to remember. And the second way is this trick. I'll tell you how to do it. The trick is pretending that this big angle is another rise over run triangle, and then subtracting the angle of beta from that big triangle. So what we're going to do is we're going to combine that angle, alpha plus beta, and do the exact same thing, tan inverse rise over run, but that rise is going to be different now. That rise is going to be 1.5 meters, right? We're talking about this rise over that entire big triangle, right? Subtract, divided by 0.75. That total angle will be 63.43 degrees, right? So where's it going? So in order to get this angle here, we need that big angle subtracted by this small angle beta in order to get that remainder angle, which is alpha. Right? That gives us that this angle is 29.74 degrees. Now we have our alpha angle, but it doesn't stop there, guys. It doesn't stop there. We need this alpha angle in radians. The reason we need this alpha angle in radians is very specifically this component of the formula requires alpha in radians, right? Because instead of like sine alpha, cos alpha, whatever, it's just alpha by itself. So it needs to be dimensionless. Unitless. Right? So you multiply our degrees by pi over 180 degrees. The degrees cancel out. That gives us 0.519 radians. Okay? That's the value we're going to plug in for the alpha in radians. Okay? So, just writing out this full equation again. All you have to note is that alpha is going to be your 0.519, but these ones, if you have your calculator already in degrees, already in radians, you can just plug in the radians again here for alpha, but I like to do everything in degrees, so I plug that in for degrees. That one's degrees, and that one is also degrees, because I haven't converted that one. Right? Make sense? Our Q was that value I said when I scrolled up before. So the strip footing has 150 kPa of loading on it. So this is just straight up given in the question, so that's fine. Right? That gives us 21.84 kPa. Right, so that is the loading, the vertical loading from the strip footing. If you're wondering what this other formula is here, don't worry about it basically, is a short answer. The slightly longer answer is it calculates the horizontal stress, but we don't care about the horizontal stress when we're dealing with settlement, which is a vertical kind of concept. So effectively, don't look at that one. Okay, we plug in our value for the strip footing and add it to our initial settlement, which we calculated, which is the combination of the soil and the raft. Got it? Okay, let's talk about void ratio and consolidation and stuff like that. So we're told in the question, the pre-consolidation stress is 50 kPa. Now, it's not the best analogy, but the best thing I can think of is this is almost like yield stress when you're talking about steel. So it's almost like the point at which your soil starts behaving differently when you add too much stress to it, right? So with that in mind, essentially, because of how our numbers work out here, oh sorry, I didn't even say what our final stress was. Our final stress after all that is 61.6 kPa. Right, so if we look at this graph, if this is 61.6 kPa, this is 50 kPa, and this is 39.75 kPa, right? Do you see how, like, from the settlement before and after our strip footing is installed, we're going to have slightly different soil behavior, right? Because, yeah, basically this portion is going to be due to this slope called the rebound index, and this portion here is going to be with the compression index. Hopefully that makes sense. Yeah, so that's how they got this formula. CR is like a slope value. CC is like a slope value as well. Yeah. So we're going to plug in everything. So this was given. This was 0.1 slope, and this is 0.4 slope, right? So all we have to do is plug in everything. This is log base 10 on your calculator. Our pre-consolidation stress was 50, and we divide that by our initial, which was this number, 39.75. CC is our compression index. I should probably write these names. And this is our rebound index. These are basically always given in the question because they're from odometer tests. They're just, like, they already did a test to find out some material properties about the clay, and they just give it to you, right? Okay, and then we have log again. Our final consolidation, 61.6 over 50. Okay? When we plug all that in our calculator, we get the change in void ratio. So again, change in void ratio just means as you're compressing down on this clay, the little holes, like the voids, pockets of air, between the clay get smaller and smaller, right? That's your reduction in void ratio. And specifically, it reduces by that amount. Our initial void ratio, which is actually, so we've actually just calculated that, right? We now have to also use this in our formula for settlement, right? We need to calculate that, right? So this is from soil mechanics, like, what do you call it? Phase diagrams? Phase something. It's equal to the moisture content. So actually in our question we're told that there's 31% moisture content in our soil. That's the equivalent of 0.31. GS is our specific gravity, right? So that's how much times heavier our soil is than compared to water, right? If we're not given it, right, we can just safely assume it's 2.65. That means that our clay is 2.65 times heavier than water. And this value, our initial void ratio, is 0.8215. Okay, so now we have both these values, so we can sub it in to this equation. And our initial void ratio is that. All right, finally, HO is the same as H, right? The O stands for original before any consolidation happens. So that's essentially the diagram that we were already given. So let me just quickly draw this out. So here's our strip footing, right? We're told our strip footing is 0.5 meters into the ground, right? The base of it. And we have a rock layer down here. So from the top surface of the soil to the rock layer is 2.5 meters. And so our H value is just going to be that, HO I guess, is going to be the difference between those two things. So that's going to be 2 meters. Right? So we get 0.025, and that's going to be in meters because H, we gave the formula in meters, so it's going to return meters. That's 52 millimeters. That's our answer. Does anyone have questions? Nope. Okay. We have 15 minutes left. We won't have time to do question 3. As in, I'll do a third question, but it's going to be question 4. So question 3 is a little bit similar to, I'll just run you through it. It looks like this. It's similar to the first question that we did, which was question 3. Okay, sorry. It's like really, it's similar to the sand question that we did, right? But the idea is that we have multiple layers, right? And we just care about the settlement of the sand. So if there's like clay at the top, sand at the bottom, we just care about the settlement of the sand, and we only have the material properties of the sand. We can use this concept called superposition, which is in the lectures and in my notes, but I won't have time to run through it, in order to calculate the settlement of the sand. It's not too bad. You're just using that S average formula for elastic settlement. Okay. So question 4 here. The idea is that the Schmertmann method is based on field testing. So maybe let's just scroll up. Sorry, I'm going to scroll up to the content real quick. There's a bunch of different field-based methods in the geotech notes, right? So if you want more detail on them, they're in the geotech notes, but we only really care about the Schmertmann method. These are applicable for cohesionless soils, in other words, for sand, and yeah, they're to do with like plate loading tests and penetration tests. So it tells you like the number of blows required for it to settle a certain amount, whatever. We're going to teach you the Schmertmann method. Right. Okay, so here's the way it works. We have a strip footing, and we know its dimensions, B and D. Oh, sorry. We know its dimension B, and it's a strip footing, so it runs into the page. It's 2 meters below the ground, and its column is loaded with 1,500 kilonewtons per meter run, right? We know that the soil is over-consolidated due to this description. This is going to matter for determining our elastic modulus using the Schmertmann method, okay? So you'll see how this plugs in a second. We have water table, 4 meters below the ground, and yeah, so the most important thing is that we're given this table, right? Yeah, so this is kind of data. So they took samples of what the soil behaves like at various depths into the ground, essentially, right? So this is what the formula for the Schmertmann method looks like, but again, we're still calculating settlement, okay? What we're going to do first is we're going to, so these are 2 constants, right? What we're going to do first is we're going to calculate, this is soil pressure, sorry, it's footing pressure. This is soil surcharge. Yeah, so we're going to calculate the footing pressure and the soil surcharge, okay? So footing pressure is based off of P. So it's off of that point load, right? Acting over your area, the area of your footing, right? So it's 1,500 kilonewtons over, our width was 2 meters and it's a strip footing, which means we're just going to divide 1,500 by 2, right? Because we're doing everything per meter run. That gives us that Q, our footing pressure, is 750 kPa, right? Next, we're going to calculate the soil surcharge. Okay, so soil surcharge, let me just draw this foundation quickly. Right, so remember, soil surcharge is a function of the depth, or like all of the soil acting above the footing, right? We know the water table is somewhere down here, but it's sand, so we don't really care. Because the water table is down here, 4 meters. Since it's sand, yeah, we don't have to account for that in regard to soil surcharge, which is a function of this stuff up here. We're given that the unit weight is 20, and our depth, as I said, 2 meters. That gives us 40 kPa of soil surcharge, right? This is just like an intermediate step, but it helps to calculate. Q minus Q naught, that's going to be 750 minus 40. Okay, so C1, right, it has a formula, right? And we've already pre-baked everything we need for that formula, and this is a constant, right? I'm going to plug in QO is 40. I'm going to plug in this bottom part as 710, right? This spits out 0.972, like that. This next constant accounts for creep, right? And we're told in the question that we have to account for creep for 5 years, right? So T is already going to be in years, so we literally just plug in 5 for this formula, and that gives us 1.34. Okay, cool. We have our two constants. That's the first step. Another thing to note down quickly is that because in the wording of the question it stated that the soil was over-consolidated, our soil's elastic modulus is going to be 6 times QC. QC is what we're given in the question, that this row here is QC, and it increases with depth. So the idea is, because QC increases with depth, our elastic modulus, or our soil stiffness, is also going to get stiffer as we go further down into the ground, right? I believe QC is something to do with kind of the pressure it takes to do something in the soil, like crush it or something. I don't know, something along those lines, right? Okay, here's where it gets a bit funky. Basically, this is a general graph that we're given, and we were dealing with strip footing, right? So this is from the geotech notes, right? It's also in my notes if you want. We have to essentially get a, the end goal is to get the end goal is to get the IZ of each layer that we care about. Yes, IZ, by the way, is our strain influence factor, right? So, by the way, this drawing doesn't represent quite our question. It's going to look slightly different. This is just a general case, right? We want the IZ in the middle of each layer that we have data on, okay? And in order to get that, we need to first calculate the peak, right? So it almost works like a triangle shape, right? This triangle shape is because it's kind of like two straight lines. One that goes upwards and it reaches the peak, and then one that goes downwards and it reaches 0, right? So this is the influence of the soil on our settlement, essentially. That's what the strain influence factor is. So at a certain point, here, we're going to reach our peak influence, some amount of depth into the soil, right? So there's a formula to calculate the peak, right, for our formula, and it's this. So we've already calculated this. This is 710. So the difference between our footing pressure and our soil surcharge. Okay. Next, this is the stress, the vertical stress at this point, right? So, so this far beneath the ground, I guess. Actually, yeah. This far beneath the ground, we want to calculate the effective vertical stress, okay, and plug that in. So, here I've drawn out kind of what our question actually does look like, right? And here we're given some variables. We're given some information about how to calculate it for a strip footing, okay? So, 2 meters beneath our footing. Sorry, our footing is 2 meters wide, right? One worth beneath our footing is going to be where we find our peak. Get it? It's going to be where we find our peak and influence factor. Z2, this is Z2, is going to be 4 widths worth beneath our footing. Okay. So Z2 is equal to 4b, which is equal to 8 meters, because our footing is 2 meters wide. Get it? Okay. So my point is to calculate the effective vertical stress, we need to go this far beneath the soil. Okay. So we need to go 4 meters beneath the soil, right? And that's also where our water table is. Okay. So in order to calculate the effective vertical stress, we can just use gamma T because it's sand and there's no capillary rise, and so we just use gamma T, the total unit weight, and not the submerged unit weight. Okay. That gives us 80 kPa. So that's the effective unit. Sorry, the effective vertical stress. Plug in 80. So now we have our max strain influence factor. If we plug everything into the calculator, it gives us this number, which is approximately 0.8. Okay. Now this number won't change for the rest of our calculations, so that's good. So once we figure that out, we don't have to recalculate it. Okay. That's what we have to sub in to these equations. So what these equations describe is they're a straight line function, right? Sorry, it actually looks like this. It's essentially a straight line function. And this first equation describes this part of the line, and this bottom equation describes this second part of the line. Okay? Hopefully this will make sense in a second. So, we're given all this data, like information, right, in the question, but only 3 of these layers will actually be useful, because past 10 meters into the ground, these won't have any influence on our settlement, right? In terms of our strain influence, they'll be like flat. So we only have to consider 3 layers here, okay? We have to consider this layer, as layer 1. We consider this layer as in from 4 meters beneath the ground to 6 meters beneath the ground as layer 2, and the remainder as layer 3. The remainder just because that's how our information was given to us. There's a spacing of 4 meters for that one, right? What we have to calculate is something called Z star. Z star is the depth from the base of the footing downwards for this layer. Z star is going to be 1 meter, right? Because the layer thickness is 2 meters, okay? And then Z star, which is the depth to the middle of the second layer, is going to be 3 meters because we've gone down 2 meters for the second layer, right? And then the depth to the middle of the third layer is going to be 6 meters because, yeah, it's halfway down this layer, which is 2 meters, and then 1 meter here. Okay. Z star is what we're going to be using in these two formulas in order to plug in and output a IZ. Okay. So in terms of how you want to set up a table, because this is a table-based method, okay, similar to like moment of area from mechanics of solids, you're gonna make a table, right? So here I've labeled 3 layers. Said the depth, which this isn't anything new. This is from the rows of the information we're given. Z star is what we just spent a little while calculating. Z star is the depth from the base of the footing to, the depth from the base of the footing to the middle of the layer. Delta Z is the thickness of each layer. Right? So the first layer is 2 meters thick, the second layer is 2 meters thick, the last layer is 4 meters thick rather, right? So QC, this is also given in the table. So QC values are this second row, okay? Right? And we were dealing with over-consolidated clay, right? Over-consolidated clay has that formula of 6QC specifically. So we literally just get this number multiplied by 6, get this number multiplied by 6, get this number multiplied by 6 to get ES, which is our elastic modulus of the soil. Z over B is like an intermediate calculation, but B doesn't change. B is our width of our footing, which is 2. So all we're doing is getting Z star, which 1, 3, and 6, and dividing it through by 2 in order to get these numbers. IZ, this is where we had to use this formula for that top layer, and the top layer was the only layer where IZ was increasing, right? Whereas the bottom 2 layers, IZ is decreasing, right? It's already reached its peak, and now it's reducing. And in which case we use that bottom formula in that table, right? And that's what we're gonna plug in for IZ. And we were plugging in to the formula these values for depth, right? Z star. Is everyone following? Maybe, maybe not. Okay, this last column in the table is specifically because this is what the final equation requires. Okay, it's just the IZ multiplied by delta Z, which is the thickness of that layer, over the elastic modulus of that layer, and then we output these numbers. We sum them together, and it gets us that number. that's that entire block which I've highlighted in the formula, this one here. That entire block is going to be equal to whatever number we got from the table, okay? So just plugging everything in again. Basically C1 was a constant value. That was the first step. C2 was the second step. That was also a constant value. Q minus QC, even easier, right? That entire block in blue, that's what we just spent ages calculating, okay? When you plug that all in, that gives you 0.151 meters or 151 mils. All right, that's the end of my workshop. So, yeah. If you have questions, come up front. Otherwise, I'll see you next week.